You know, in every sci-fi movie, they just hit a button and go faster than light. But have you ever wondered, why can't we do that in real life? What's stopping us? Well, it's not about building better engines. It's about a fundamental rule of the universe. So let's get into it and figure out why there's a cosmic speed limit. Look at this number, 299,792,458 meters per second. That's the speed of light in a vacuum. We call it c. And it isn't just really fast, it is the absolute unbreakable speed limit of the universe, period.
So, the big question is, why? Why this number? Why can't anything with mass ever reach it? This isn't just some technological hurdle we'll overcome one day. No, this rule is woven into the very fabric of space and time itself.
Okay, so to understand a speed limit, you've got to understand the thing setting the pace, right? So first things first, what exactly is light? What is this thing we're trying to outrun? Way back in the 1860s, a physicist named James Clerk Maxwell figured something incredible out. He discovered that light is an electromagnetic wave. And here's the kicker. Its speed has nothing to do with the light itself. It's a property of space. It's determined by fundamental constants of the vacuum. In other words, the universe itself dictates how fast light travels through it. And this is where light gets really, really weird. It has this dual identity. Sometimes it acts like a wave, rippling through spacetime, and other times it acts like a particle, a little packet of energy called a photon. This whole wave-particle duality thing is absolutely key to understanding why it's so special.
And that brings us to the photon. Here's the most important thing you need to know about it. It has zero rest mass, absolutely none. Think of being massless as the ultimate VIP pass to travel at the cosmic speed limit. Because photons have no mass, they don't just get to travel at c, they have to. It's the only speed they can go in a vacuum.
So, we've got a massless particle whose speed is built into the fabric of space. That's a huge piece of the puzzle. But then, along came Albert Einstein, who took that one fact and wrote a completely new rulebook for how the universe works. In 1905, Einstein dropped his theory of special relativity, and it all came down to two simple ideas. The first one makes total sense. The laws of physics work the same for everybody who isn't accelerating. Easy enough. But the second rule? Well, the second rule is where things get completely wild. It says the speed of light is the same for everyone, no matter how fast they're moving.
Let that sink in for a second. If you're on a super fast train and you throw a baseball, its speed adds to the train's speed, right? Simple. But light breaks that rule. If you're in a spaceship going at half the speed of light and you turn on your headlights, you'd expect the light to move away from you at, well, half the speed of light. But it doesn't. You and a person watching you from Earth will both measure that light moving at the full speed of light, c. It's totally counterintuitive, but it's been proven again and again. Now, for the speed of light to stay constant for everybody, something else has to change. And that something is reality itself. As an object with mass, like you or a spaceship, gets closer and closer to light speed, the universe starts to warp. Time for you actually slows down compared to someone standing still. You physically shrink in the direction you're moving, and the energy it takes to make you go just a little bit faster starts to go through the roof. And this chart shows you the ultimate problem. As you get closer to c, the energy you're pumping into your ship stops making you much faster and starts making you more massive. So pushing that now heavier ship gets harder and harder. Getting from 99% to 99.9% takes way more energy. And to hit that final 100%, well, it would take an infinite amount of energy. And since there's no infinite energy source lying around, it's literally impossible. You know, this speed limit isn't just some random cosmic rule. It's actually a safety feature. It protects causality, that simple, crucial idea that cause always comes before effect. If you could travel faster than light, you could break this rule. You could send a message to the past. The universe would be full of paradoxes. So the speed limit is what keeps reality making sense. So, okay, this isn't just a bunch of weird physics equations. This cosmic rule has huge, real-world consequences for us, especially for how we explore the universe. This timeline really drives home how mind-bogglingly big space is. Even at the fastest speed possible, a message to the moon takes over a second. A radio call to Mars, you're waiting about 12 minutes for a reply. And the nearest star system? It's a 4.24-year trip one way for a signal. Interstellar conversations are not going to be happening in real time. But there's a really beautiful flip side to this. Because light takes time to get to us, every time we look up at the night sky, we're looking back in time. The light from the North Star left 323 years ago. The Andromeda Galaxy? That light has been traveling for 2.5 million years. Our telescopes aren't just looking out into space, they are literal time machines.
All right, now for the really fun part. We know we can't break the rule. We can't travel through space faster than light. But could we maybe bend the rules a little? What about all those sci-fi ideas?
So, here are the greatest hits. A warp drive doesn't move a ship through space, it moves space around the ship. A wormhole is basically a tunnel, a shortcut from one point in spacetime to another, and tachyons are these imaginary particles that are born already going faster than light. The problem? Well, there's always a catch. They all seem to require bizarre things like exotic matter or negative energy, which we've never seen and might not exist. So for right now, this is all pure theory.
Quantum entanglement. This one comes up a lot. You have two particles linked, and what happens to one instantly affects the other, even if they're light years apart. So, instant communication, right? Well, no. The connection is instant, sure, but you can't actually control it to send a message, so no FTL texting. Causality is safe once again.
At the end of the day, after more than 100 years of experiments, the verdict is in. From the first attempts to measure light speed in the 1800s all the way to our giant particle accelerators today that get particles unbelievably close to C, every single piece of evidence we have says the same thing. The limit is real. It holds up.
So when you really think about it, the speed limit isn't some frustrating barrier holding us back. And it's not even really about light. It's about the fundamental architecture of our universe. It's about how space, time, and causality are all woven together. Light just happens to be the thing that travels along the seams of that fabric at the maximum speed the universe allows. It's not a rule to be broken. It's the structure of everything.